Hey everybody, and welcome back to Calc 3 Online. Today I just want to go through a few problems that I kind of think are harder and I think will act as good review for the end of Unit 2 here. So all of these use like different kind of tricks related to vectors. We're going to use things like some of the formulas that we've learned with like magnitude of the cross product and even like what the cross product means, and you'll see. So this first problem is at first glance kind of weird, and then it actually turns out to work out really nicely here. So the goal is to show that these specific four vectors, if you add them together, you get 0. And if you read here, so it says let v1, v2, v3, v4 be vectors with lengths equal to the areas of the faces opposite the vertices P, Q, R, and S, respectively. Okay, so what that means is v1 should be opposite P, okay? And the direction is perpendicular to the respective faces and pointing outwards. So basically, V1 would look like that, pointing kind of out of the face QSR, like that triangle, and it's the opposite one from P. V2 would be opposite Q, so all these are like perpendicular to perpendicular. So that's V2. V3 would shoot out this way. And V4 is kind of like pointing down, but I don't think I'm gonna do it because it will be like too hard to sort of draw it. But basically it's like underneath. This is, some sort of tetrahedron pyramid, and it's pointing sort of straight down into my page. So that's the V1, V2, V3. I'm also gonna just let I'm going to call it like A is equal to PQ. I'm going to let B equal PR. Whoops. And C be PS. So we've got A, we've got B, and we've got C. Okay. So, based on like the definition of these vectors, we know that actually like something like take V2, let's say, would actually be equal to 1/2 B cross C. And the reason is, the way I define these two vectors right here, they are in this triangular plane, PRS, and the V2 vector is perpendicular to that plane. So for sure, like if you cross B and C, you're going to get like V2. The reason it's half is because it's equal to, where's that line? I'm just looking for. Here we go. So the vectors have lengths equal to the area of the faces, and we know that like when we do cross product, the vector is basically equal to the parallelogram that's formed by the two. So since it's equal to like the triangle, we just have to chop it in half, and that would be equal to the area of that triangle. And for like the same reasons, we would have like V3 equals 1/2 C cross A, and then V4 would equal 1/2 A cross B. And the one that I'm not talking about yet is V1, and that's just going to take a little more work. So probably the easiest way to do this, honestly, is to let me kind of draw, I guess, over here. So what I want to show you is that QS equals actually B minus A, and I want to show you that no, wait, sorry, I looked at that the wrong way. QR, and I want to show you QS equals C minus A. Okay, and it's probably easiest if I just draw it. So take QR there along the bottom, that vector. So these are vectors. If I go down that side PR, and then I go, from there I go minus A, which would just be the opposite direction. So this is B, and then this is minus A. This vector up here, right, that's going to be parallel. This is going to be parallel to QR down here, and they're really the same vector. Like the distances match up and the directions match up. So QR is B minus A. And you could do the same thing for QS, but I think once you see one of them, you could kind of believe this other one too. So I've got QR and QS, which are vectors down here in terms of A's, B's, and C's now. So I could take V1 and using the same kind of idea as up here, I know that any of these vectors, based on this fact that it's equal to the areas of the faces, have to be half the cross product of two vectors in that plane. So V1 is going to equal like 1/2 C minus A, and then put some parentheses in there, crossed with B minus A, because QR and QS are two vectors in that plane that V1 pops out of. If I simplify this a little bit, you can distribute with the cross product, that's fine. So I'm going to do that, and I'm going to get C cross B. I'm going to get minus C cross A. Then I'm going to get minus A cross B. And then I'm going to get positive A cross A. So that's just expanding this part out, right? So this thing right here would go to 0, that last term, because if you think again that, cross product gives you, like the cross product of two vectors gives you the area of the parallelogram formed between them, then if you're crossing a vector and itself, there's no parallelogram like this. So this should be the 0 vector. It has to be. Okay, so I now have forms of all the vectors V1, V2, V3, V4 in terms of A, B, and C. And actually, if you go and just add them all up now, you will actually see that they equal 0. So we got 1/2 C cross B minus C cross A minus A cross B. And then that's V1. And I'm going to add to that 1/2 B cross C. I'm going to add to that 1/2 C cross A. Add to that 1/2 A cross B. All right. And maybe I will also, I should probably distribute that 1/2 in. So I'm gonna distribute this in quick too, which I think will make it more clear. Okay, so let's look at what we have here. We've got a negative 1/2 C cross A and a positive 1/2 C cross A. We've got a negative 1/2 A cross B and a positive 1/2 A cross B. And then we've got this 1/2 C cross B plus 1/2 B cross C. But if you remember, one of the things I had you do in a video was look at this C cross B versus B cross C, this kind of idea. And we saw that the term for this cross product is what we call anti-commutative. And what that means is this actually equals 1/2 negative B cross C if you flip it around. And so then if you add it to 1/2 B cross C, you're going to get 0. Which is kind of a cool problem. It uses a lot of like tricks that we've used in this unit, so it's a good one to know. So another important thing from this unit is just doing these distance between plane problems. And so I just want to go through another one of these right now. So I'm going to start by drawing a picture. So let's see, we have this purple plane, and then we have this blue one. And they're definitely parallel because the normal vector for the purple one could be written as -2, 4, -6, if you just move that 6 over. And then the normal vector for the blue one would be, let's see, we'll do it 3, 6, 9, if you move these x and y's over, okay? It's going to bug me. There we go. So you can see, oh wait, I moved that over wrong. This should be -6. There we go. But if you look at it, which is what I did when I noticed that was wrong, these are actually scalars of each other, right? So if they're scalars of each other, their normal vectors point in the same direction, and so the planes are parallel. So I want to start by getting a vector that kind of connects the two. And in the purple plane, you could always, because there's no like term with just a number, there's like just x, y, z, you could then take the point 0, 0, 0, definitely is in that plane, right? Like 0 equals 0 is the idea. Then in the other plane, I think I will take, I'm just doing math in my head here. So I see that 1/3, 0, 0 is in the plane because so I'm thinking of it again as 3x minus 6y plus 9z equals 1. And if I make those 0, 3 times 1/3 would be 1, right? So I have a very nice vector here. I'm going to call it v. V would be, we could just call it -0 minus, I don't like the minus, so I am going to change my arrow to go this way because I like positive numbers. Okay. So I'm going to get that vector, just calling it then 1/3, 0, 0. And now I really have all the stuff I need. So the idea is like I'm going to project, I have like this normal vector, like this, let's say. And the idea is that normal vector might not perfectly span the distance between them, but if I project this red vector over onto it, then for sure it's going to like stretch out and be perfectly the actual distance between these two planes. And then I could just find the magnitude of it and I'll be done. So I'm going to do the projection. So I'm going to project vector v onto the normal, which would really just be like, let's see, not that bad for the top because we're just going to do 1/3 times -2, which is going to be -2/3 up there. And then the rest of it would be 0 because of these zeros here. And then we would have n dot n on the bottom, so that's going to be 4 plus 16 plus 36. And then all of that is just times the vector -2 for -6. And if you just take the magnitude of that projection, then you should have the answer. And if you do it out, it's about, I guess I should use a little about symbol, it's about 0.089. That's how far apart those planes are. So this problem I just want to do because there's an area of math called differential geometry that I used to do a lot of stuff with, and to me, when I see this equation, my brain just can't help but see a sphere, and I just wanted you to see why that thing is a sphere. Now that you know vectors, you should be able to kind of follow with this. So this is actually how most people in like engineering and physics and stuff write equations of spheres, which to you probably doesn't look like a sphere at all, but actually if you just go through the computation, it is a sphere. So I wanted to show you. So these are just general like 3D vectors. Like this is your kind of variable vector, and these are just more specific like point vectors. And if we just go through it, so we would have this first part would just look like x minus a1, y minus a2, z minus a3. And then this part would look like x minus b1, y minus b2, z minus b3. And if we just dot and set equals 0, you're going to see that everything actually just boils down to be an equation of a sphere. So actually, I'm not going to quite do that part yet. I'm going to just do the dot product stuff out here. So x minus a1 times x minus b1 plus y minus a2 times y minus b2 plus z minus a3 times z minus b3. And then I'm just going to distribute. Okay. So now what I'm going to do is I'm going to group some like terms. So you have like, you have some x terms here, you've got some y terms here. So basically I'm just grouping these guys, these ones, and these ones. And then that would turn into, let's just do a different color. That would give me x squared. I'm going to put all the squared terms in the front too. So I have an x squared, y squared, and z squared. Then I would have like negative b1 minus a1 times x. I'd have minus b2 plus a2 times y. Then I'd have minus b3 plus a3 times z. And then I could move like all of these constant terms over to the other side, and well, let's not do it yet actually, so let's just keep it right here. And then we got plus a3 b3. Okay, so if we, this thing was set equal to 0 just by definition up there, and so what I was sort of saying before is if you move this whole part right here over to the other side, it kind of fits your style of like a sphere. Like it would look like something like x squared, y squared plus z squared plus, some number times x plus some number times y plus some number times z equals like 4 or something like that. And this is, a perfectly fine equation of a sphere that you could like complete the square on if you wanted and like get the center. But it is kind of weird. But and we could talk about the geometry of this if you want, but why that should give you a sphere, but it really does. And I kind of recommend you actually think about why this thing is giving you a sphere, if you can think about the like picture of it. But that is an equation of a sphere in vector form. And if you go study a bunch more vector calculus and stuff, you're very used to seeing that as a sphere. So another problem here that's just kind of a bunch of different concepts that I think are good to go through. You've got basically just these three separate pieces, but they do all share this one fact that A cannot be 0 in them. And they're basically just yes or no questions. So let's do this. So a lot of these you kind of just need to be like clever, I guess, about and think about a little bit. So this first one, if you dot two things A and B and it equals A dot C, do B and C like have to be the same thing? The answer to that is no. For example, you could let like A equal I hat, and you could let B equal J hat, and C be 0 vector. That definitely makes that not true, right? And there's other cases too you could definitely do, but that seems like a simple one. If A cross B equals A cross C, then does it follow that B equals C? Okay? And for this one, I kind of think about the idea of the parallelogram. So again, if you take like A cross B, then the cross product is really giving you the area of this parallelogram. A cross B equals the area of that parallelogram. So if you kind of keep that in mind, you could just take vectors like A could be, 1, 0, 0, and B could be 2, 0, 0, and C could be 3, 0, 0. And all of those are parallel, so those cross products here would be 0, but definitely B and C are not the same thing, right? So basically it's like you just had a vector, and then you had another vector, and their cross product is going to be 0, but those two vectors don't have to be the same. So the answer to this one is, again, no. The last part here, so if A dot B equals A dot C, and A cross B equals A cross C, so we're kind of mixing parts A and B, then does it follow that B equals C? And the answer is yes. And let me show you why. So if you take the dot product one, A dot B equals A dot C is going to imply that like A dot B minus A dot C equals 0, and so A dot B minus C should equal 0. And then I would basically, you can use like the cosine kind of definition of dot product. So that should be equivalent to the magnitude of A, magnitude of B minus C, times the cosine of the angle between them is 0. And we know that we're given, that A doesn't equal 0. So this part is not how we're going to kill off that term. So basically what that means is that this or this needs to get me the 0 part. So either magnitude of B minus C equals 0, or theta equals like pi over 2 plus n pi. And that's kind of all we know from that part. Then the cross product part, if you do A cross B equals A cross C, then I'm going to do the same kind of thing where I'm going to subtract over one of them, and then I'm going to sort of factor that A out. And then now I'm going to use the sign formula that goes with cross product, basically. So we know that this implies that the magnitude of A times magnitude of B minus C times the sine of the angle between them is going to be 0. And again, it can't be the A that's doing it, so I'm going to get rid of that. So here we either have magnitude of B minus C equals 0 or sine of theta equals 0. But both happen. We were told that both have to happen. And so this doesn't equal 0 when this equals 0. So then the only thing that could be is basically this magnitude of B minus C is 0. So if the magnitude of B minus C equals 0, then it's not hard to see that B has to equal, whoops, just blew it right there. B equals C. So the answer to this one is